sunum yapacağım. Hiç yapmadım bu sunum daha önce. Umarım olur. İlginizi çeker. Sorularınızı da heyecanla bekliyorum şimdiden. Müsaadenizle başlayayım.
Lütfen. Bekliyoruz.
Hocam sesimi duyabiliyorsunuz değil mi? You can hear me.
Evet, gayet iyi duyabiliyoruz. Gayet iyi.
Okay. Perfection. Okay. So, good morning. I think good afternoon for you in Turkey. So, I'm going to talk about shape sensitivities for thermoacoustic stability of annular combustors. And this is my content of the presentation. I will start with introducing the concept of the thermoacoustic instability, not in very much detail, and I will talk about my methodology, and I will discuss my results, and I will finish with conclusion. So, the high amplitude acoustic oscillations in combustion chambers within the rocket engines or gas turbine engines can cause several structural damages like this. So this is the combustor right after the manufacturing, and this is the combustor after 6 months of operation. And as you can see, this combustor is damaged because of the acoustic oscillations, the uncontrolled acoustic oscillations within the combustion chambers. So that damage is caused by generally sound waves, as I mean acoustic oscillations. And the growth rate of the thermoacoustic oscillations is sensitive to many geometric and flow parameters. For example, my geometry is affecting the acoustic oscillations growth rate, and maybe injection time delay is also affecting the acoustic oscillations growth rate. So I need to change them to stabilize my system. So the challenge is to identify these changes cheaply and accurately at the design stage. So before manufacturing the combustion chamber, I need to understand what should I change, but by doing that, I need to make this cheaply and accurately, which is difficult. So to do that, we use adjoint methods, and using adjoint methods, just a single calculation, we can predict the sensitivities of the growth rate and frequency with respect to the shape parameters. And our previous group member, Jose Aguilar, has shown that this adjoint-based shape optimization works well for network model. The network model is just 1D acoustic model. So you are modeling the pipes starting from here, then from here to here, you are applying area change, and so on. This is not very detailed acoustic modeling, but this is the most simple modeling method you can get in the literature. And he applied this adjoint-based shape optimization method to this combustor. The black combustor is the initial geometry, and the red combustor, as you can see, is the optimized, stabilized geometry. But in my study, I modeled this combustor using my Helmholtz solver, and I'm gonna explain what is Helmholtz solver. So before that, the Stefano Falco, who is also a previous group member in my group, is introduced that shape optimization for thermoacoustic instability using finite element based Helmholtz solver. And he used B splines to parameterize the geometries for this combustor, for example. This is the inlet of the combustion chamber, and it was perfectly rectangular at the beginning, and you are seeing the stabilized design with red boundaries, and the dots are the control points which controls the geometry of the combustion chamber. So after doing these changes, so the red design becomes stable, numerically of course. And The gradients of the control points can be calculated using just single calculation using adjoint methods. Otherwise, we had to move that control points each time by finite difference method. So we need to repeat the calculations, for example, 30 times because I have 30 points. But using adjoint methods, I use only one calculation to calculate the gradients of the eigenvalue with respect to this shape changes very quickly. So in the first place, I solved the thermoacoustic Helmholtz equation, and this is simulating the acoustics in the combustion chamber, the left-hand side. And the first term on the right-hand side is representing the fluctuating heat release rate, which is flame in my case, and fluctuating body force, which is the second term on the right-hand side, is simulating the damping caused by the cooling holes. And I also solved the momentum equation at the same time. And I am using finite element method to discretize these equations. So I quickly talk about the choked boundary conditions because in the real combustors, so we have like Mach numbers of 1 in the inlet of the combustion chamber and outlet of the combustor chamber. So the combustor chamber is placed between the turbines and the compressors, and exit of the compressor is choked inlet, and before the combusted gas before entering the turbine is choked outlet. So from these boundaries, I have some acoustic energy loss, and I need to consider that when I simulate my acoustics of the combustion chamber. And we also need to implement a block boundary condition because the most annular combustors have a discrete rotational geometry. I have this gray sector, this is called sector, and I repeat that sector 16 times in the clockwise direction, and I get full annular combustion. But if I use block boundary conditions, I just use this single sector, and I apply block boundary conditions to the azimuthal component. I don't need to simulate all of the combustion. I just need to simulate this combustion, and I can get the full eigenmode of the combustion. And the first application of the block boundary condition was introduced by Georg Mensa, I think 4 years ago, in his PhD thesis. But I implemented this block boundary condition in my Helmholtz solver as well. But I'm not going to show any result here. And the cooling hole modeling is done with the Cummings model. So I consider this part, this rectangle part, as a fluctuating body force. The body force is going and coming from left to right or top to bottom. So I model the acoustic energy loss from the holes, the cooling holes. And I also incorporated this into my Helmholtz solver. Then in terms of shape derivatives, which is the most difficult part in my thesis, so I calculate the direct and adjoint eigenfunctions of the combustor using solving thermoacoustic Helmholtz equation. And I calculate the derivative of the eigenvalues to the shape changes in Hadamard form. So which is kind of a weak form in finite element. So I calculate the derivatives of the control points or surfaces, and I change the position of my surface or control points to stabilize my system. So if I'm going to give an example, the shape derivative is a complex number because I'm dealing with eigenmodes of the acoustics. So my problem is a complex eigenvalue problem. And I calculate the derivative, the shape derivative of the boundary, and it has a real and imaginary component. And if that, for example, if the real part of the gradient is positive, that means if I move that boundary in the normal direction, it's going to increase my eigenfrequency. And as we can see, so if I increase the length of the pipe, it's gonna increase the frequency. But the real part of the eigenvalue is representing the eigenfrequency of my system. But I need to deal with the stability of the system, so I care about the imaginary part of the eigenvalue. So if the imaginary part of the shape gradient is negative, this is my original design, and I have a negative shape derivative, negative complex part I have, and if I move that boundary in the normal direction, it's gonna decrease my growth rate, which is what I want. So I need to increase the length of the combustion chamber. But if I have positive, that means if I move that boundary in the normal direction, I am gonna have increased growth rate. So I need to make the pipe smaller. So I need to make the changes according to signs of the shape derivatives, basically. It's very important. So to talk about my Helmholtz solver, this is my favorite slide because I spent 2.5 years to make my project fully open source, and I exploited all the open source projects around the internet. So I first generate the geometry with FreeCAD using Python scripts, and I mesh my geometry, the complex geometry, with Gmesh, which is also open source finite element measure. And I discretize my mathematical partial differential equations with Phoenix X, and I derive the weak forms. And I generate the matrices with PETSI, which is parallelized C matrix generator and solver. And at the end, I'm gonna get eigenvalue problem to find the eigenfrequency of the system and eigenmode of the system, eigenfunction of the system. And I use SLAPC for that. And at the end, as I'm solving very big problems, I had to parallelize my solver, and I used OpenMPI library to parallelize my solver. So to sum up, the main steps of the shape optimization procedure are: I solve the direct and adjoint Helmholtz equations with my Helmholtz solver, and I calculate the shape derivatives, and I update the geometric parameters according to shape derivatives. And I'm gonna look if my system is stable, I stop changing the geometric parameters. But if not, I go back to the here, then I go down again. So to demonstrate the results, I have 3 test cases, which the first one is simple geometry, and the second one is relatively complex, and the last one is the most complex one I get. So I implemented the choke boundaries because I have acoustic energy loss from these boundaries, inlet and outlet here. And this is the most simple example I can get in the literature because there are very limited number of examples. And I got this example from LOTA, which is one-dimensional acoustic network model, which Rolls-Royce uses every day. And I try to verify my choked boundary implementations by implementing this reflection coefficients at the inlet and outlet. And I have a flame sitting here, and this is the injector point. And first, I run passive calculations. The passive means that I don't have any temperature change. Basically, there is no flame. And I get this frequency from LOTA, this frequency from my Helmholtz solver, and these are the growth rates I get from these two different tools. And when I put the flame in, the temperature is changed. The temperature starts to increase from here and decrease to the outlet. And it changes the stability of the system. In this example, I get stable system, but the whole point I'm trying to make is I'm trying to get the same growth rates using 2 different tools. So this example shows that my Helmholtz solver is correctly modeling the choke boundaries. And for test case 2, this is also taken from Lotan. Lotan is modeling this complex geometry with one-dimensional ducts. So at the end of the, like when you run a Lotan test case, you can't see this combustor. It is just junction of pipes, the connection of pipes. But in my Helmholtz solver, I can generate this geometry, 3D geometry, and I define my boundary conditions and fluctuating body force, which I'm going to talk about now. So I use Neumann boundary conditions except the inlet and outlet, and these are the choke boundaries. For these yellow volumes, I implemented a fluctuating body force because we also have some acoustic energy loss because of these cooling holes, because there is flow separation here, and I need to take that into account when I calculate my eigenvalue. So I used 250,000 elements within a half sector mesh. I only simulate a half sector because for this example, I am trying to compute the axial mode, not the azimuthal mode. So I only need the one sector, actually half sector. And I applied mesh refinement for these dilution holes. And this is my temperature field. This is highly discontinuous because in Lotan, we don't have nice temperature field. So because it is one-dimensional code, and from that point to that point, you can only implement one temperature, and from that point to that point, you can implement one temperature. So this is because, so this is why I have this discontinuous temperature field. But for fluctuating heat release rate, I can model this heat release rate distribution, and for the injector behavior, and this is called measurement zone, I implement this Gaussian function here. For these two functions, I can use Gaussian functions. And these are the real and imaginary parts of the direct and adjoint eigenfunctions. And I'm going to use these functions to calculate the shape derivatives now. For this example, I am going to calculate the shape derivatives on the surfaces. And so I'm not going to make any changes for this case, but I find the shape derivative of the eigenvalue with respect to the surface deformations, not the mesh points, just all the surface. And these are the real and imaginary parts of the shape derivatives of the eigenvalue. And I want to stabilize my system, so I need to deal with the imaginary parts of the shape derivatives. So this is this is unsurprisingly, so we can see that the most influential part is the dilution holes, because so this is, I have a negative shape derivative on the boundary of the dilution holes, which means that if I move the boundary in the normal direction, I'm gonna get lower eigenvalue. So that means I need to increase the diameter of the dilution holes. So this is, frequently encountered in the combustion chambers because they are putting so many dilution holes to simulate acoustic energy loss. And my last example is mica combustor, which is extensively studied in the literature. So I have combustion chamber, I have flame sitting in the combustion chamber. This is the sector view of the mica, by the way. And I have these two other components, perforated plate and burner. And this blue section is plenum. This section is plenum. But for this example, I define entire geometry with NURBS surfaces. So these points you can see on the screen are controlling the shape of the combustor. I generated the entire combustor using these points. I think there are maybe 40 points in total, and using that 40 points, I can get this complex geometry. And I again use Gmesh to mesh this geometry, and I applied mesh refinement near the measurement point because I am calculating the gradient of the test function here, so that needs to be very accurate. And I release the heat within a finite cylindrical volume here. The red zone is the heat release zone. And these are my inputs. So, I mean, you don't need to understand that. So this is the magnitude and the phase of the flame transfer function. And this is the temperature field of my combustor. As you can see, after flame, my temperature is peaking at the flame and it's going down to the end. But before the flame, it's only 300 Kelvin. And these are the real and imaginary parts of the eigenfunction. And I calculate the direct and adjoint functions. This is direct eigenmode, and I also calculate adjoint eigenmode, which looks similar to this. And I use them to calculate the shape sensitivity of the NURBS points this time. In the previous example, I was calculating the shape derivatives of the surfaces, but this time I'm calculating the shape derivatives of the control points. And this is the animation of the eigenmode. This is unstable eigenmode because the growth rate is positive. And we can see after some time the acoustic fluctuations are increasing by time. This is, by the way, maybe 100 milliseconds or something. So these are growing very quickly. As you can see, the high amplitude acoustic oscillations are surrounded the combustion chamber, which is very unwanted in the real life. And I find the shape derivatives of the eigenvalue with respect to the control points, not the surfaces, control points. And these changes, these vectors, shows that if I move that boundary in the direction of the arrow, I'm gonna get reduced growth rate. So I need to change my shape according to these vectors. So it's gonna result in like this curvy shape, and for that boundary, this curvy shape, for that boundary, I'm gonna get something like this. But these gradients are not as strong as here. So I will slightly move that points in the upward direction to reduce my growth rate of the eigenvalue. And after some iterations, after 5 iterations, I get this sector geometry, the green one. The initial geometry was having that growth rate, 528 radians per second. And when I do the shape changes, I can continue to do that, but in this case, I'm just showing. When I do these changes, when I get to green boundaries, I'm gonna get this growth rate, which is smaller compared to this. And this is my like deformed combustion chamber after some changes. And when I do these changes, the phase difference, which is controlling the combustion instability, is increases. So this is the initial data of the burner taken from the burner. The phase difference data from each burner. I have 16 sectors, and my phase difference is around 80 58 degrees, but when I do the shape changes, it's going up to 68. When I get 90 degrees, I'm gonna get fully stable system. But I didn't do that for just sake of demonstration. So the conclusion, I implemented the dumping caused by cooling holes and choke boundaries in my Helmholtz solver, and I parallelized my Helmholtz solver, and I parameterized the geometry and the gradients of the eigenvalue with respect to the geometric parameters. And the parameterized combustor geometries are made more stable or less stable by changing the geometry in line with these gradients. And my feature work is I'm trying to apply this procedure to complex combustion geometry. And in my models, the models I shown you are very simple models. So I need to make more sophisticated burner modeling to capture the growth rate more accurately. And these are my references. And thank you. Thank you for listening. This is the end of my presentation.
Okay, thank you very much. That's a, that's a great presentation. Çok teşekkür ediyoruz.
Rica ederim
Sanırım
hocam.
aramızda yabancı olabilir. Bu arada bu yayını, yani bu sunumunun Twitch üzerinden canlı yayınladık. Bilemiyorum şu anda dinleyen var mıdır, yabancı var mıdır? I would like to thank anybody who watched this over Twitch, but we will continue our discussion in Turkish from now on. Sorry folks, if you do not understand. Ekrem, çok teşekkürler. Ben sorular için açıyorum. Arkadaşlardan sorular olmuştur mutlaka kafalarında konuyla ilgili. Benim de var ama ben daha sonra sormayı tercih ediyorum. Önce arkadaş.
I'm very happy to help you if you have any questions. By the way, I can show the presentations as well because you might refer the page number if you have a question.
Sure. Yes, that would be great. If you
okay, let me try to figure it out. Okay, single section. All right, can you see the presentation?
Yes, we can.
Perfect.
So who would like to take the floor first?
Okay.
I can take. I think the mic is here, right?
Mic is here, right?
I can go there. I think we are continuing in English.
Yeah, we are continuing.
Hi, Ekrem. It's very nice to see you again. Mete here.
Thank you.
We missed you already. So, in the 13th page, you showed two cylinders. I guess, yeah. And you told us that the imaginary part is actually defining the stability of the geometry, right?
Yes.
Did I understand it right? Okay,
Correct.
So I think this is a fundamental property for cavity acoustics, I guess. There's something I didn't know, and I think it's an important knowledge for us to understand. So I understand that we can design some cavity and look to its acoustic sensitivity from the imaginary part. Did I understand that right? Or
yes, this is exactly what I try to explain.
Oh, okay, that's fine. So it means I think I understood it right. And also you say that as you increase the cavity volume, the eigenfrequency decreases, right? So if when you change that eigen frequency, so you are not interested in only the first mode, right? Maybe you are interested in some other modes as well. So what is the span of that? What is the eigen modes that you are interested in? First 10 modes, first 20 modes, or 200 modes?
Mhm.
I don't know. Maybe if you don't want to give these information, by the way, it's cool. I'm just asking from curiosity. You are. I think you should be free to not answer at all.
Hocam, there is no top secret in this presentation. So
Okay.
I changed the geometry, yes, with respect to the complex part of the shape derivative of the eigenvalue. And I can do that for any mode because in my Helmholtz solver, I specify a target eigenfrequency and my solver is trying to converge that eigenfrequency. And when I find that eigenfrequency, I can get its eigenmode and I do this shape optimization. So the answer to your question is I can find thousands of modes. So it's just like I just specify a target and my Helmholtz solver is trying to go that target and it finds eigenvalue and eigenmode. I I can do shape optimization for any mode. That means
But isn't that sensitive to the mesh size of your model?
yes, but you're right. So I mean I can't compute all the eigenfrequencies at the same time. I guess. So you're right.
Hmm.
I mean it
But
will
you
take
are
long
limited
time.
with the CPU capacity, I guess. So you
Yeah,
can solve anything, but you are limited with the CPU capacity.
exactly. But so in my case, for example, the Rolls Royce knows which frequency is unstable.
Hmm.
So that means,
Hmm.
I mean, for that reason, I'm just calculating the one frequency.
Okay.
But there might be other modes which can be unstable. So
Hmm.
you're right. I mean, in generally, the thermoacoustic instability for thermoacoustic instability problems, it's generally known that the unstable eigenfrequency is known, but they don't know what to do. They don't know what to change. So my PhD thesis is trying to show you need to change that part of the geometry to suppress that frequency. I'm not sure if I answered it.
No, I think you just satisfied anything that I asked. Thank you very much. And also, that's my last question. You also showed us some video for
Yes.
your mode shapes, and you said that those displacements are increasing with what? That's the question actually. Was it changing with time, or are they different geometries that you generated that you optimized? I didn't understand that part. This one, okay.
So this is only shows the eigen mode. I mean, I don't have any shape optimization. Actually, I
Hmm.
should move this slide to here. Sorry, I'm doing this for the first time.
Okay, no problem.
It's confusing, I know, because I mentioned about the shape derivatives, then I showed this. It's not relevant. I mean, but this is the just eigen mode of this frequency. I mean,
Okay,
I
but
don't
I
show.
think
Yeah.
I think you said that it is increasing. It's increasing its displacements, amplitudes.
Hmm.
I think something
Okay.
said like that, but maybe I misunderstood. Maybe.
No, no, you're right. So as you can see, this is I normalize this eigen function. It has a maximum of one here and maximum of one here. And by the time goes on, if you see that it is increasing. I mean
So
that
okay, it's a
one
time-dependent
goes to
analysis.
back. That
Yeah.
one. So
Okay.
I couldn't rescale this in ParaView. So if I rescale this, it is most probably going to be 5. The maximum value is going to be 5 because I have positive growth rate. So acoustic oscillations are increasing. The magnitude of the oscillations are increasing. I'm trying to show that in this animation. I'm sorry if it's confusing.
Okay, okay. I just didn't understand that this was a time-dependent analysis. Now everything's clear.
Hmm. Okay. Do you have
Okay.
any other questions?
No, that's me. Okay, it's fine.
I,
I'm
I
leaving the floor.
guess I guess there are some other questions.
Buyurun. Soru soracak olan kişi. Başka
Questions.
kim isterse.
No questions? Okay.
Yani şeyi
I have
sorabilirim
a question.
belki.
Okay, you ask.
Yani Mete abinin sorduğu şeyle ilişkili. You said that they know the unstable frequency. How do they know this frequency? By experiments or by some analysis?
They put speakers and microphones, and they are listening the signals, the sound signals of that frequency, and they can determine the frequency from the microphones. But this is not the microphones we use every day. These are like sophisticatedly calibrated microphones, very expensive microphones. And when you receive the signal from the microphones, you do FFT, which is called fast Fourier transform, and you can determine which frequency is peaking. And we are trying to find that mode in my Helmholtz solver, and I change the geometry of the geometry of the combustor.
So in the process of measurements, is the engine is running or is it off? So I think it is running, right?
It's running in the test batch uh, according to some operation conditions, but they can't place the microphones inside the combustion chamber because it's very hot. But it doesn't matter. The sound waves can travel through the boundaries of the combustion chamber, and they are putting microphones on the combustion chamber from outside. We can see the microphones, and they listen.
Thank you.
Any other questions, Ufuk? I think.
Yeah. Ekrem Hocam, it's very good to see you again. And thanks for the presentation. It's a great presentation. I have one question for this video, actually. So, as far as I understand, this is a transient simulation, right?
So I calculate the eigenmode. Eigenmode is just the one moment. I mean,
Yeah.
I have a frequency and I calculate the eigenmode. But if I do eigenfunction times e to the minus I omega t,
Yeah.
and if I scan the t from 0 to 10 milliseconds or something, I get this frequency. I get this animation.
All right. I see. One thing is which solver do you use in solving eigenmodes?
Yes, good question, detailed question. I used PEP solver, which is called polynomial eigenvalue problem of Slepsy.
Oh, okay. So
PEP solver.
I think this solver is a new one, right? Which comes with Phoenix X because as far as I remember, it
Yes,
it isn't appearing in Phoenix Legacy Phoenix.
yeah, no. So actually, I generate the matrices in Phoenix, and after that, I don't use Phoenix at all. I just use Slepsy. I use Phoenix to derive the weak forms and assemble the matrices.
Oh,
And after assembling the matrices, I don't use Phoenix at all. But
uh,
I use Phoenix X, and this is complex problem. So my matrix size is less than yours.
okay. So do you call this library Slepsy from outside Phoenix, right?
Exactly.
Okay. Which language do you use for that?
Python.
Oh, again Python. Okay.
They have a Slabc 4Pi.
All right.
So you first install the C code of the Slabc, then you install this to call the Celebsi functions from the C code.
Yeah,
So
thanks.
I don't write in C code. I just
Okay,
use
okay.
Python.
Yeah.
I didn't mention that. Maybe I should.
All right.
Okay, thank you.
No
Any
problem.
questions, Ufuk?
Thanks.
Any other questions?
Yeah. For actually at page 9, you mentioned block boundary
Yes.
condition. Uh, I will just ask a short question about that. So, for this problem, I guess you use periodic boundary conditions, right?
Yes.
In the radial tangential direction.
Exactly. And I use Dolphin-X MPC.
Okay.
Multiple constraint.
Multiple constraints.
But how do you implement block boundary condition? Yeah.
I mean, this is technical question. So as I showed,
Maybe I can turn it into a little more non-technical, because can I contribute to your question, Ufuk?
Yeah, of course. Sure.
Um, I would ask, what kind of wave vectors are you using in the block type? I mean, are you changing the wave vectors in direction, or the wave numbers? Are you playing with the wave numbers, or how do you decide on those?
I play the wave numbers, uh, and wave numbers can be defined. For example, how many sectors do I have in example? If I have 16, the wave number, I couldn't remember exactly now, but the wave number is, I don't know, 2 pi divided by sector numbers or something like that.
I see. I see.
So I impose, if I have one here, I need to have two here, like
I
something like
see.
that. So this is the definition of the block boundaries. You know exactly what you have, the block boundaries, like you know the relationship between these two boundaries,
Right.
and you are just imposing this as a constraint.
Right.
And yes, in this example, it's wave number. You're right, hocam.
By the way, if you didn't use block boundary conditions, but instead you just used periodic boundary conditions, would you still be able to get a useful solution without block, but just periodic?
Hocam, I use block boundaries. I mean, block
Okay.
boundaries are also called periodic boundaries in my case.
Yeah, I see, but you are right. But block boundary um is like I mean, it is kind of an enhancement of the periodic boundary conditions, as far as I understand it. You can have periodic boundary conditions without block conditions, because the block conditions are like the displacement u of x is going to be equal to e to the power kx times the displacement at ux plus r type of thing. But even without that, you can have some simpler periodic conditions. That's why I was wondering.
Okay, hocam.
So another question, if nobody else has questions, is when you implemented the NURBS, of course, is a good idea to change the geometry. Did you use like isogeometric finite elements, or did you use normal finite elements?
I just use Phoenix, hocam, but
Okay.
I I generated this geometry in Gmesh, and
Yeah.
Gmesh offers you, so when you define these points and when you generate the mesh, for each mesh point, I can get the parametric coordinates u and v. I'm not sure if it's clear. It's complicated.
Yeah. No. You use normal finite elements. You didn't use like an isogeometric finite element, which makes use of the NURBS curves, as far as I understood from your answer. Another question I had is like in your results, did you get a non-axis symmetric geometry as a result, or did the axis symmetry change? Because the lower portion seemed to have a different curvature compared to the upper portion. So I thought that it became an elliptical part instead of the circular
Mm.
part.
Oh yes, exactly. So I get non-axis symmetric changes with respect to this axis. But
Interesting.
I mean, I changed the geometry, axis
Are
symmetry.
you, is this
So
because of the gravity?
no, hocam. I don't know. It's just because of these gradients.
Hmm,
Um,
very.
I didn't thought about the physical, like the gravity actually.
Hmm.
I mean, I have 12 sectors in this case, but I can, for example, I mean, how can I explain? So if I apply these changes to one sector here, but if I don't on this here, so it's gonna
Mm-hmm.
be highly non-axis symmetric.
Mm-hmm.
But in this case, I apply axis symmetric changes in the clockwise direction. Maybe.
So final comment or question is
Mhm.
like if you change or suppress a problem in a certain eigenmode, then you surely have to check the remaining eigenmodes, right? Because they change or they shift in the same time, right?
You're right, hocam. Yes.
Okay. Thank you very much. These are
I
my
can also contribution.
yeah. Özgün, our young uh, our youngest participant Özgün.
Okay.
Hello.
Hi.
My question revolves around you compensating for like one frequency. If so, do these engines or these devices have to be compensated for multiple amounts of frequencies, or if so, if they were to be compensated around multiple frequencies, would you choose like the most damaging one, or would you compensate for overall?
So there is a trade-off between the most dangerous one, but generally we are trying to suppress the most dangerous one because this is most likely to happen. But if we have very close to most dangerous, so then we do trade-off between the changes. Like we implement two-shape optimization procedure and we do the trade-off between these two. So we are trying to maximize the stabilization. I mean, we are trying to maximize the optimization.
I understand.
Mhm.
My last question was the same as Fethioja's last question. So if you were to compensate for one of them, it wouldn't just make the situation more complicated to go on and try to compensate even more for like more failures.
Mhm. Exactly. Fethioja was right because when I change the shape of the combustor, the other eigenmodes change, the frequencies change, uh, but generally 90% of the time. So we knew that we knew the unstable frequency, and we play with that frequency. I mean, but you're right. So other modes can be more dangerous when I change that frequency. When I change my combustion according to that frequency. So this should be taken into account actually. Thank you very much for the note. Very good question.
Okay, thanks.
Mete has one more question.
Yeah, it's not a question, but maybe a kind of a contribution, and it's very related to what you both talked about. So I think it is the same thing that I'm going to say, but from a perspective of architectural acoustics. Actually, in architectural acoustics, there's a criteria named Bonello's criteria, and when you are trying to design a space, you try to make the number of modes as much as possible in the lower frequencies. So I think this maybe can be applied to this problem as well. So you can check the number of modes within the lowest modes that you are checking in, and you try to get rid of the coloring. They call that in architectural acoustics coloring of the modes, because if you leave some mode alone in some frequency, and usually it's the case in the lower frequencies, you have one frequency and then the next mode's frequency is wider. The frequency range is wider, and that frequency range decreases. The band between the mode frequencies decreases, and at higher frequencies you have many modes almost very adjacent to each other, so there's no coloring in there. But when you have single mode in lower frequencies alone, say that it's alone, it is away from the next mode's frequency, it has higher amplitude, and it has more distinctive characteristics to hear for the listeners in architectural acoustics. But maybe I am making some assumption here. Maybe it can be relevant to that project as well. So you try. Bonello has I think 2 or 3 criteria. So he says that the modes should not be repetitive on up to each other, because it will just increase its strength. But they should be close to each other within some band. And he says that the frequency distribution should be increasing monotonically. There are some criteria, so it's worth checking maybe.
Interesting.
Yeah.
Hey, Bajan, thank you very much. It's a good note.
Thank you very much.
My
Ahmet
pleasure.
Hocam, any questions from our external participant?
Honestly, I wait a question from Ahmet Onur.
Merhaba. Türkçe olarak devam etmek istiyorum mümkünse.
Tabii ki. Buyurun.
Please do.
Sanırım yabancı bir katılımcı yok. Twitch'i de kontrol ettim.
Süper.
Ben daha çok bu yanma odasının mekanik ve yapısal kısımlarıyla ilgilendim yaklaşık 4 yıl kadar. Kullandığınız yanma odası tipini tam anlayamadım ama hani bizim ilerlediğimiz tip RBQL denen bir tasarım aslında. Primary zone ve secondary zone'da farklı termal durumlar oluyor. Sizin yanma odası modelinizde ben ön tarafta sıcaklıkların fazla arkaya doğru azaldığını gördüm. Normalde secondary zone'da daha sıcak bölgeler olabiliyor. Yani bu yanma odası tipine göre değişiyor aslında. Şimdi ben bunun biraz aslında biraz yorum yapmak gibi olacak benimki sorudan ziyade. Bu işin biz daha çok Life'a etkisini inceliyoruz. Firmamızda bununla ilgili testler yapılıyor. Ömer Faruk birlikte de bakarız. Çok yüksek sesli, gerçekten yani tüm fabrikadan duyulabilecek şekilde bir uğultu oluşuyor. Sanırım sizin bahsettiğiniz test oydu değil mi? Yanlış anlamadım Ekrem Bey.
Yani o ses akış sesi mi emin değilim ama benim bahsettiğim yani bilmiyorum, fabrikayı görmem lazım herhalde. Şöyle,
Belki ziyaretçi mümkündür, bilemiyorum. Konuşuruz onları da. Burada sizin belirlediğiniz kritik modları biz mekanik olarak aslında harmonik incelemeler yaparak belirlediğiniz frekansları parça üzerinde excite etmeye çalışıyoruz. Excite ettiğimiz zaman oluşan mean ve alternating streslerin life'a olan etkilerine bakıyoruz. Ama sizin bu thermoacoustic instability ile ilgilendiğiniz kısmı bizde aerodinamik mühendisleri bakıyor. Böyle bir bilgi verebilirim. Genel olarak çalışmanız çok güzeldi. Ben çok ilgiyle dinledim baştan sona kadar. Çok farklı. Burada daha çok sizler kodlama, matematiksel modeller, işte open source vesaire benim çok yabancı olduğum şeyler açıkçası. Ömer Faruk'a da daveti için çok teşekkür ediyorum. Burada dilution hole olarak bahsettiğiniz soğutma delikleri farklı farklı şekillerde modelleniyor yanma odalarında. Yani impingement hole, dilution hole, effusion hole, quench hole, bunları duymuşsunuzdur muhtemelen. Neden özellikle dilution hole'lar üzerinde çalışma yaptığınızı merak ettim.
Evet, güzel bir soru. Dilution holes en büyük delikler. Aslında şöyle, Sizin dediğiniz problem, ya aslında bu olayın gerçeğe uygulanması zaten şu an yapan insan yok gibi. Bir tek Fransa'da Serfax diye bir merkez var, biliyor musunuz?
Yok,
Safran
hiç
var.
duymadım.
Safran diye bir şirket var.
Safranı biliyorum. Hı hı.
Onlar bu
Safranı
combustion
biliyorum.
işini bayağı iyi biliyor.
Hı hı.
Onlar bütün kodları elde tutuyor. Bir de en kompleks geometrilerle yani en kompleks geometrileri tasarlayan, bu alanı domine eden ekip onlar, anladığım kadarıyla dünyada.
Hı hı.
Bizim alanda da en iyi doktora tezleri Fransa'da yapılıyor, ekolde. Onlarda, ya benim solver'ımda bu zaten yeni bir şey. Yani bunu Helmut Solver'da daha önce yapan maalesef ben göremedim. O yüzden ben buna çok zaman harcadım, bunu yapmak için, kodlamak için.
Hı hı.
Neden bunları yapıyorum? Çünkü bunlar en büyük delikler. Bu delikleri meşleyebiliyorum. Çok büyük oldukları için.
Hı hı.
Normalde senin dediğin gibi cooling holes, diffusion solve falan da var ama onlar çok küçük. Onları meşlemeye kalkarsam benim problem çok büyüyor. Matematiksel ve kodlama olarak. O yüzden işin içinden çıkılmaz hale geliyor. Onun yerine biz o effusion hole'ları akustik olarak boundary condition olarak modelliyoruz.
Hı.
İşte yansıma katsayısı olarak, reflection coefficient olarak. Ama meşleyebileceğimiz bir büyüklükteyse delik, onu meşliyoruz ve işte bu modeli kullanıyoruz.
Anladım.
Ama dediğiniz
Burada
doğru.
amaç burada amaç aslında yani siz bu delikler üzerinden ilerliyorsunuz ya.
Hı
Amaç
hı,
bu deliklerin hangi parametreleriyle oynayarak termoakustik instability'yi iyi yönde etkileyebiliyorum. Aslında bunu tespit etmeye çalışıyorsunuz.
hı hı.
E, Peki şöyle bir sorum daha olacak. Bu da son sorum olsun.
Tabii.
Biliyorsunuz işte yanma odası üzerinde çok fazla delik var.
Hı
E,
hı.
bu deliklerin birbirlerine olan etkileri de var. Aslında bu nasıl diyebilirim? Kombine bir şey. Yani
Evet.
sizin burada çapı değiştiriyor olmanız instabilite açısından faydalı olabilir ama bunun bir sonraki sırasında bir delik varsa kötü de etkiliyor olabilirsiniz. O zaman çıktığı nasıl kullanmamız gerekecek? Onu merak ettim.
Onları işte sizle yan yana oturup karar vermemiz lazım.
Anladım. Yani
Çünkü
multidisipliner olarak anladım.
bu aşırı multidisipliner. İşte CFD'cinin sağ yanımızda, structural'ın sol yanımızda olup, ya bu zaten çok ileri bir problem aslında. Yani bunu dediğim gibi hani Türkiye'de var diyorsunuz. Bu güzel bir haber. Çünkü burada mesela işte biz şu an bahsettiğim gibi o sizin anlattığınız combustion chamber geometrisi bende var. Ee, ve onun tasarımı bunlardan çok farklı. Bunlar sadece akademik uygulamalar. Yani
Hı hı.
akademide bunları yapabilen yok. Yani
Yuvarlak,
hala yok yani.
basit geometri.
Yani basit geometri,
Hı
basit de
hı.
ilk başta bunu modelleyip sonra bunu taşımak. Şu an benim yapmaya çalıştığım zaten o doktoramın sonuna geldi. Ama
Yok, çok çok güzel bir çalışma. Bölmüş gibi oldum. Kusura bakmayın. Bizde var dedim ama şöyle biliyoruz demedim. Ya biz de öğrenmeye çalışıyoruz. Bizim aerodinamik ekiplerimiz de öğrenmeye çalışıyorlar. Yeni yeni bunların testleri yapılıyor. Ee, Onu belirtmek isterim.
evet ya, yani benim hocam da 30 yıldır falan bu işle uğraşıyor ama hala kimse bu işi bilmiyor diyor. O yüzden sıkıntı yok. Uğraşmaya devam.
Evet.
Çok sağ olun cevaplarınız için.
Siz sağ olun. Teşekkürler katılımınız için. Çok kıymetli. Endüstri bakış açısı.
Rica ederim, ne demek.
Biz
Sizin
böyle
yaptığınız iş çok kıymetli.
uzaklaşıyoruz
Çok sağ
işte
olun.
ne demek. Fethi hocam da bilir, nümerik kod yazmaya başlayan adam dünyadan soyutlanıp, değil mi hocam?
Zaten bir de mühendis olmak var. Hem mühendis olup hem de nümerik kodla olunca tam oluyor yani.
Bir de Linux hocam.
Bir de Linux, evet. Ama inşallah Linux dominasyonu yakındır. Penguen yapacak dünyada. Çok teşekkürler. Harika bir konuşmaydı. Bizi acayip renklendirdi. Beraber çalışmaya mutlaka devam edeceğimizi düşünüyorum. Biz de grubun ismini açık kaynak sayısal mekanikti daha önce. Açık kaynak sayısal akustik ve mekanik olarak bu sene güncelledik. Ve işte çok benzer workflow'lar üzerinden çalışıyoruz. Yanma vesaire gibisinden kompleks konular bizde yok ama yapma potansiyelimiz belki ileride olabilir. Çok fazla zamanını almayayım.
Estağfurullah. Ya bu şekilde hocam, bu sunumu da ben ilk defa yaptım, o yüzden ya dün de yolculuk yaptık, işte dünden önce de bir
Hı hı.
vize başvurusu yaptım, ondan çok da
Süper.
çalışamadım, kusura bakmayın.
Süper. Estağfurullah.
Anlaşılabilir.
Çok güzeldi.
Çok keyifliydi.
Bu arada hazırlamış olduğunuz, Ahmet'le hazırlamış olduğunuz sonlu elemanlar temelleri kursunu dün yaptıramadık. Çünkü 2 öğrencimiz vardı ama aslında sizin tutorluğunuza ihtiyacımız var. Belki onu siz yerleştikten sonra bizim öğrencilerle bir deneme yaparsınız, bir test run yaparsınız. Yani nasıl gidiyor diye, aslında en güzel yöntemi o olur diye düşünüyorum. Yani insanlar canlı olarak öğretirken sıkıntılarını da görürsünüz, sıkıntılı taraflarını. Bir gün öyle bir şey ayarlayabiliriz. Şey yaptığınız zaman, yerleştiğiniz zaman bize haber verirseniz onu ayarlayabiliriz.
Olur hocam ya, çok iyi olur.
Tamam.
Ben onu gününü şaşırmışım hocam. Ben onu bugün sanıyordum.
Ya dün akşamdı ama başka bir gün yaparız. Hiç sıkıntı yok. Biz dün akşam başka problemler üzerinde uğraştık.
Tamam.
Özgün bir şey soruyor.
Son bir sorum daha var benim. O merak ediyorum cidden.
Ses geliyor mu acaba?
Çok az geliyor.
İstersen bu tarafa.
Hocam bu arada virtual setup'ınız harika.
Kusura bakmayın, en sonunda bir daha soruyorum ama bu işte mesela kompanse ediyorsunuz ya hataları ve zararlı frekanslara. Bunları fazladan yapma gibi bir sıkıntı var mı? Onu merak ediyorum. Overcompensate etme gibi bir korkunuz.
Onu yapınca işte şey olabilir. Bu Ahmet Onur Bey'in bahsettiği şey başka şeyleri etkilemeye başlayabilir. İşte aerodinamik performanslar, structural performanslar, işte ısı transfer yönetimi. Onlar falan zorlaşabilir.
Anlaşıldı.
Ya bu böyle çok multidisipliner, çok eksenli bir çalışma. Benimki sadece bir kısmı ve ya ben bu dizaynı bu değişikliği yaptığım anda bu değişikliği soracağım 3-4 tane insan var. Ya ben bunu en son elime geldi. Bunu değiştirip üretelim diyeceğim bir şey değil. Yani bunu değiştirip hemen iterasyonun başına gidip işte aerodinamikçilerle, yanmacılarla hepsiyle konuşup ondan sonra en son yani bunu üretmek lazım.
Hı hı.
Bu şekilde.
Çok teşekkürler.
Çok teşekkür
Tekrar
ederim.
görüşmek üzere.
Rica ederim hocam. Çalışmanız bizi de motive ediyor. Buluşmanız, workshopunuz.
Aynen, seni de bekliyoruz mutlaka buraya.
Bekliyoruz mutlaka,
Gelecek sene.
evet.
Birlikte olalım
Hocam
burada.
hedeflerimiz büyük. Dünya haritası arkamda. Dünyayı ele geçirme planlarımıza
Aynen.
kalarak.
Öyle.
Tamam hocam. Görüşmek üzere. Size kolay çalışmalar. İyi günler.
Teşekkürler.
Çok teşekkür ederiz.
Merhaba
Onur, çok
tekrardan.